All right. So good afternoon. Welcome to the Compass seminar series. I'm happy to introduce Gage Banner from Canada. Canada's been a basin of attraction for us lately. Gage got his PhD in mathematical physics with a focus on stochastic processes from the University of Madison.
Yeah.
Okay. His advisor was Jean-Luc Tifo, and he graduated last year in August, and his dissertation thesis was entitled Random Entanglement and History-Dependent Random Sequences. Today, Gage is going to be talking about progress on a subject that we introduced him to, and he's going to be applying ideas from Markov chains that he applied in his thesis that he's an expert on.
Thank you very much. Thank you very much, Javier. Yeah, thank you very much, everyone, for coming. Hi, everyone on Zoom. I haven't forgotten about you. So today I'm going to tell you a good amount about transition path theory and also a good amount about Sargassum. The thing about transition path theory is that it's sort of steeped in the theory of Markov chains. So I actually do want to start off with a review of kind of the basic calculation methods and tools from Markov chains, and hopefully try to convince you that doing transition path theory is better than not doing it, essentially. Let me start off actually with a quick definition. So a discrete time Markov chain is a sequence of random variables, so x1, x2, x3, etc. It's a sequence of random variables such that the distribution of the next step conditional on the entire history is equal to the distribution of the next step conditional on the most recent step. So that's what we call the Markov property. And if you have a stochastic process with the Markov property, you call it a Markov chain. But okay, so the idea, the intuitive idea behind a Markov chain is you have something that's happening randomly, and the distribution of what happens next is random, but we only have to look at where the state is now. We don't have to care about the entire history. So it's nice when you can model your stochastic process as a Markov chain, because it means that you have a long history of relatively powerful calculation tools available to you. And as I say here, it's in general a stochastic process can be very, very complicated, but at least if you have a Markov chain, you don't have to think about the entire history. So that's why we care about these things. My favorite example of a Markov chain is the board game Snakes and Ladders. Snakes and Ladders is a children's game, also suitable for research scientists. And it's kind of a funny game because you don't make any decisions. You just roll the dice, and if you land on a ladder, you go up the ladder, and if you land on the head of a snake, you go down the snake. You don't actually make any decisions. You just try and get to the end of the board. But it's a Markov chain because it doesn't matter how you got to a specific square, right? So if you're at 9, the distribution of where you go next doesn't depend on whether you roll a 5 and then a 4 or a 6 and then a 3. The point is you're at 9 now. Okay, so it's a Markov chain. What about something that's not a Markov chain? Unfortunately, almost everything, it's actually a bit hard to find a real-life example of something that's truly 100% mathematically a Markov chain. A lot of things are approximately Markov chains, or Markov chains in the appropriate limit, but it's a little bit tricky to find something that's exactly a Markov chain. But you can still use it to approximate things, which is what we'll see later. So in a valiant attempt to make this kind of fun, I'm going to tell you about the calculation tools of Markov chains in the context of gambling. So I want to talk about blackjack. Blackjack is a classic casino card game. It's also called 21, where the goal is to increase the total of your hand to at most 21 and outscore the dealer. So you're playing against the house. And I want to consider a simplified version of blackjack where at each hand the same kind of thing happens. So that way we actually get a Markov chain. So in this particular case, I'm going to impose these probabilities. So let's say that you're playing blackjack, and at each hand, the probability that you win is 42%, the probability that you tie is 8% and the probability that you lose is 50%. These probabilities are actually true to life. You know, on a typical blackjack hand, if you play optimally, these are actually true to life probabilities, which should be intuitive because the house isn't going to run a game that you have a better chance of winning than losing, right? You're always going to lose on average. By the way, if you think this is all trivial, let me put this question to you. Is real blackjack a Markov chain? So this is a Markov chain because I made it a Markov chain, but a question for you is real blackjack a Markov chain? I think that's actually kind of non-trivial, and I'm not going to tell you the answer, but it's something to think about. Anyway, in this particular case, just to make it small and simple, we're gonna play this kind of game. So let's say that we start with 3 chips. So we have 3 chips, and we play. You know, we win some, we lose some. If you get to 0 chips, we're gonna open our wallets and buy another 3 chips and start over. If we get to 6 chips, we're so excited that we buy a round of drinks for the table and then we go back to 3 chips. This is, of course, just to make sure that the Markov chain kind of circulates, right? So we're always playing it over and over again. But when you think about it, it's actually not so different from the way that people actually gamble in casinos. So maybe it's not that bad of a model. Okay, and this is what it looks like. So this graph up here is a visualization of the nodes in the Markov chain. Each node is labeled with that number of chips, and the blue arrows are showing you the transition probabilities. So if you look very closely, you can see that on the top row from 1 to 5, the probabilities of going left are very, very slightly darker than the probability of going right, because I said the probability of losing was bigger than the probability of winning, right? And there's also these very, very small self loops, like here, encoding the probability of a tie. So it's a Markov chain. Now, the question is, what happens in this Markov chain? So I set this up. Probably the most interesting question in my mind is, what fraction of the time do you spend winning versus losing, right? You care about whether you win or lose. So what fraction of the time are you spending in the lose state, which is 0, and what fraction of the time do you spend in the win state, which is 6? So one way to answer that is to just simply simulate it. So here I'm showing a simulation of this Markov chain for 10,000 hands, if you like. And each of these lines shows the lose and the win state. So let's look at the blue line. What you see here is there's kind of a big transient where it spikes up and it oscillates pretty wildly. But then eventually it actually settles down to a relatively flat level around maybe 6% or so. So what that's saying is, in the long-term behavior, you spend roughly 6% of the time in the lose state, like you just lost all your chips. And similarly, you spend roughly, in the long term, roughly maybe 3.5% in the win state, where you have 6 chips. So that's the simulation, that's the observation, if you like. Another question then, how do you actually explain this? So this is cool and everything, but the question you can ask is, how come these lines converge? How come it goes up and it does these wild oscillations and then it goes flat? Why doesn't it just keep oscillating? Good question. So to answer that question, we're going to need a tiny bit of theory, but don't worry, there's absolutely no equations, it's just words. So the first definition I have for you is the definition of an ergodic Markov chain. So a Markov chain is ergodic if, for any initial condition, if you wait long enough, there's a non-zero probability of being anywhere in the state space. So it's a bit hard to conceptualize this. The easy way to think about it is, you need to have a Markov chain that has no islands, which means that you can't have a Markov chain where there are nodes that are kind of by themselves somehow, that aren't connected to the chain by transition probabilities. If there are nodes that are somehow by themselves, this doesn't work. Or if you have a part of the Markov chain that cycles. So if there's a loop in the Markov chain that you're sort of stuck in, that doesn't work either. So as long as it's connected and mixes itself, then you have an ergodic Markov chain. Another definition, a stationary distribution is a probability distribution. Okay, so it's just weights, right? It's percentages on nodes. It's just a series of weights on these nodes. And it has the property that if you achieve it, meaning if you at some point are actually in the stationary distribution, it sticks. So if you're in the stationary distribution and you play a hand, you'll still be in the stationary distribution. And now I can hit you with the, if you like, the fundamental theorem of ergodic Markov change, which is just that if a Markov chain is ergodic, then it converges to a unique stationary distribution. So it's actually a very powerful and pretty general result, considering that the condition it needs to satisfy is actually not that strong. And to bring that back to our blackjack example, so the point is, all we need to do is to establish that this is an ergodic Markov chain. So, okay, I wrote here, it is ergodic, but why is it ergodic? Remember, the conditions were that I can't have islands. So there can't be any nodes that are somehow by themselves and not connected to the rest of the chain. And if you look at the arrows, you can see that there's no node that isn't connected to the rest of the graph. Similarly, there are no loops that I'm forced to take. Of course, you could go in a loop, but the point is you're not forced to take the loop. So as long as there's no islands and there's no loops, we're good to go. We have an ergodic chain, and therefore the ergodic theorem applies. Therefore, we should expect the fractions of each state to converge to the stationary distribution. So in order to actually calculate that, we just need to do one thing, which is not too complicated. All we need to do is create the transition probability matrix. So this, it's a relatively big matrix. It's a 7 by 7 matrix, one row and column for each of the 7 states. And all I've done is put those probabilities that I told you into this matrix, right? You see those numbers I flashed earlier, 50%, 8%, 42%. These are all just the transition probabilities. All I do is I stick those in a matrix, okay? And the matrix somehow encapsulates the playing of a hand. So every hit of that matrix is like playing a hand. So going back to the graph that I showed you, we can actually calculate something now. So if pi is a stationary distribution, it's a vector. Traditionally in probability theory, pi represents a vector, which is a bit confusing if you're not in that world, but it's only going to be on this slide, so we'll sort of power through. But in any case, so if pi is a stationary distribution, by definition, the only thing I told you is that if you're in the stationary distribution, you stay in it. So in other words, if I'm in the stationary distribution and I hit it with a transition, in other words, I play a hand, I have to get back to that same distribution, right? This is the entire defining property of the stationary distribution. But then if you look at this, what is this actually saying, right? If you look at this equation, what is it saying? What it's saying is simply that pi is an eigenvector of p with eigenvalue 1. Okay, so that's a easy condition for calculating the stationary distribution. So we all know how to calculate an eigenvector. It's a straightforward calculation, and you find this. So let's actually compare these numbers to the graph. So this leftmost entry here is the lose condition, right? It's the zero chip condition. This is 5.9%, and this converges to around 5.9%. This is the win condition, 3.5%, and this converges to around 3.5%. So it works. So that's pretty cool. And there's one standard visualization is to actually color the nodes by their stationary distributions, and that's what I've done here. So it's the same graph, but now the redness is indicating the weight of the stationary distribution. So you can see that 3 has the biggest weight, and that should sort of make sense because you're coming back to 3 a lot. Every time you win or lose, you're coming back to 3. So you spend a lot of time in 3. And you spend a little bit more time in 2 than 4 because you're going left a little bit more than you're going right. So these colors sort of jive with the underlying transition probabilities. Yeah, so that's really it for the basic analysis tools of Markov chains. Of course, you can compute many different things, but this is the gist of it. So now I actually want to move on to explaining how we are motivated to think about transition path theory from this. And again, to make this as interesting as possible. What's more interesting than gambling? Cheating at gambling. Yeah. So actually, I'm going to introduce a Markov chain that involves cheating, and blackjack is unfair, right? So maybe we don't feel that bad. So I'm going to modify this Markov chain to include this cheating, and I'm going to do it in a specific, vaguely contrived way, but it'll make sense. So let's say that we start with 0 chips, and by 0 chips, I don't literally mean you have nothing, just an initial condition, right? Just label it as 0. So we're starting with 0 chips, and we're going to decide whether to cheat or play fair. So just flip a coin in our brains and say, okay, this time I'm going to cheat. This time I'm going to play fair, etc. Okay. So you decide whether you're going to play fair or cheat, and so let's say you decide to play fair. You play fair until you get back to 0. So you win some, you lose some. Eventually, if you get back to 0, then you repeat that process, or you get to 4 chips, which I just made the win condition, and then you go back to 0 and you keep playing. Okay. So it's sort of a decision Markov process in a way. And I'm going to doctor the probabilities a little bit. So if you play fair, I'm going to use the same probabilities that I just used, right? The 50% and the 42%. If you cheat, though, you're going to get a higher chance of winning because you're cheating. Yeah. However, I'm also going to introduce a very small probability of getting caught. So there's going to be a small probability of getting sent back to 0 chips if you take the cheating path. Of course, in real life, if you cheat, the casino is probably just going to kick you out. But that's why we do theory and not experiment. Okay, so this is the Markov chain that I just described. There are numbers behind this. I'm not going to show them to you because it's just a big list of numbers. But let's just look at the graph because it's a lot easier to understand. So we start here. We start at 0. We decide with a fair coin flip whether to take the high road and play fair, F for fair, or take the low road and do C for cheat. It's very funny, the high road and the low road. Yeah, I thought about it. Anyway, so if you take the fair route, you go, it's the same probabilities I just mentioned, right? You go right versus left with roughly equal probabilities. If you take the low road, you can see that the rightwards probabilities, these blue arrows, are much stronger, which is what I talked about. It's going to give you a higher chance of winning. However, hopefully this is visible. You can see these leftwards arrows down here that are pointing from these lower nodes back to 0, which is like the cheating, tax, if you like. Okay, so this is the Markov chain, and in fact, I've pre-analyzed this. You'll notice the nodes are already colored according to their stationary distribution. I've already done that. So everything I just talked about with the eigenvector and everything, that's already done. So for example, what you can see here is in the long term, you spend most of your time at 0, again, which should make sense because you're coming back to it a lot. And you spend the second most amount of time in 1F, which is a bit interesting. Because you play fair and you cheat with the same probability, right? So why would this be asymmetric? Why would this node be darker than this node? It's not obvious, but essentially the point is that these nodes are pushing you left more than these are pushing you left. So this node gets a little bit more weight. Yeah. The thing about this is, and this is where I'm going with all of this, is that the basic analysis tools of looking at the stationary distribution don't tell you, in some sense, which paths you're actually taking to win. So in other words, of the times that you win, the times that you actually make it from 0 to 4 chips, which one are you doing? Are you going upstairs or are you going downstairs? This doesn't tell you that. It just tells you where you are in the long term. Okay. To answer the question of which paths are actually being taken of the winning paths, you need a more advanced framework, and that is this transition path theory. Okay. So what is transition path theory? So I'm going to hit you with another definition. Let A and B be non-intersecting subsets of a state space of a Markov chain. So in other words, they're just some amount of nodes. It can be one node, it can be a set of nodes, whatever. As long as they don't intersect and they don't touch, you're fine. Just any sets in your Markov chain. We think of A as being a source and B as being a target. So the whole thing of transition path theory is that it tells you about getting from a source to a target. So you need to impose those. Another definition, so we say that a trajectory through a Markov chain, and to be clear, a trajectory is just a sequence of realizations of the random variables. Okay, So xn plus 1, all the way to xn plus l. Those are just steps, right? Just sequences of steps. We call that chunk of steps reactive if it starts in A, right? So xn is in A. That means the first step of this is in A, and it ends at B, okay? So xn plus l, that's the last one, is in B, and A and B are not visited at any other time, okay? So what does that mean? It means that the trajectory left A, it didn't hit A or B, and then it hit B, okay? The whole point of reactive trajectories is that they don't take detours, they don't wander around. They have committed to leaving A and hitting B. Those are the trajectories we're interested in. We're interested in the case where you have a source and you have a target and you hit them, okay? So to summarize that, TPT is a framework which allows us to calculate statistics on reactive trajectories. That's it, that's all it is. So we want to look at these reactive trajectories and calculate stuff about them. So because the reactive trajectories are so important, I do want to waffle a little bit about what they actually are. So what I'm showing you here is just a cartoon, right? This winding line is a cartoon through an abstract Markov chain, right? So you're taking all these steps, you're going this way, that way. Sometimes you're in A, sometimes you're in B, sometimes you're between them, right? You're going all over the place. Which segments of this tour are reactive? So I've highlighted the reactive trajectories in red. So why is this a reactive trajectory? This is a reactive trajectory because it leaves A, it starts at A, it hits B, and in between, it doesn't hit A or B. Same thing up here, right? It leaves A, doesn't hit A or B, and then hits B. Those are reactive trajectories. This thing over here is not part of the reactive trajectory because it's still deciding, if you like. It's still deciding whether to go to B. It's like, am I in A? Am I not in A? It hasn't quite figured it out yet. But these trajectories have committed. Okay? So those are the trajectories we're looking at. So given that we have restricted our attention to this subset of all trajectories, of which there are many, what can you calculate? So there's a bunch of different statistics, but I'm just going to tell you about the basic ones. You can calculate the reactive density. Okay, the reactive density is just that. It's the distribution of states that these trajectories actually find themselves on. So delete every trajectory except the reactive ones. Where are they? That's the reactive density. The forward current is if you like, the gradient of the reactive density. It shows you which way reactive trajectories are flowing. Okay, so in general, those point from A to B, but not always, right? There can be very complicated paths depending on your Markov chain. And you can also calculate the time. So what this tells you is, again, of the trajectories that are reactive, which is a subset of all trajectories, how long does it take them to go from A to B in numbers of steps? Okay, so these are basic quantities that you can calculate using TPT. And there are formulas for these things. Okay, the formulas are not so complicated. They involve inversions of matrices. They're linear systems, so they're not so complicated. I'm not going to bother showing those. Instead, I'll just show you the results because it's easier and more fun, I think, to just look at the result. So this is our cheating Markov chain, but I've done transition path theory on it. So let me explain to you what we're actually looking at here. So to do TPT, you need a source and a target. Okay, those need to be imposed. You need to put those in there. Transition path theory isn't going to tell you what they are. You need to put those in there. So what's the source and what's the target? In this case, it's actually pretty clear. The source is going to be 0 and the target is going to be 4. Right? I want to see how am I getting from 0 to 4. Then the orangeness of these nodes now corresponds to the reactive density. So what this is telling you is the oranger the node, the more time reactive trajectories actually spend at that node. Similarly, the greenness of these arrows, the thickness of these arrows, is telling you the strength of the forward current. So the stronger the arrow, the higher the current through that path. Similarly, I found that the transition time was 5.82 steps. So to compare this to what we just calculated, so I think this is helpful because it shows you what's actually happened. So this up here, this red and blue one, was the original Markov chain with the transition probabilities and the stationary distribution, right? This one down here is the Markov chain that I've already done transition path theory on. So what transition path theory has actually done is it has said, okay, of the trajectories that make it from 0 to 4, okay, of the reactive trajectories, the favored path is actually this one. So this is, somehow saying that cheating is better than playing fair, which is really the take-home message. But yeah. So, and that's the end. No. Now, in some ways, this might not be that impressive because I think so. The natural criticism, let me preempt the criticism, is aren't you just kind of deleting the arrows that are going left? Like if you just look at the top graph and delete the arrows that are going left, don't you just kind of get the bottom graph? And almost, you have to be a bit careful though because the densities are certainly not the same. Right? The densities look completely different. So in this example, sure. In this example, sure. You can say, okay, the transition probabilities are bigger downstairs, so that's going to have the higher current. Fine. So, however, what about this? What about that? So now what are the transition paths? My point is, if you have a very, very complicated Markov chain, and in real life you have a Markov chain with hundreds, thousands of states, what's the transition path? You need these analysis tools to actually pick them up. So, for this very complicated Markov chain, by the way, we're past the gambling thing. These are just probabilities. This is no problem for TPT, and TPT shows this, which is very interesting. This shows you there's actually 3 dominant transition paths. There's 0 to 2F, and then 2F to 4. There's 0 to 1C, 1C to 2F, and then 2C to 4, or 2F to 4, excuse me. And then there's the most interesting one, which is 0 to 1F to 3F, backwards to 2F, and then to 4. So you see, it's really not just picking the probabilities that get you to your target as fast as possible. It must be doing something more complicated, right? Which this example kind of demonstrates. But again, to be clear, transition path theory, and this is something you really have to keep in mind when you're doing it. If you impose a source and you impose a target, which is what you have to do, it will always find a path if one exists, right? And it must exist because it's an ergodic chain. It will always find a path, okay? So transition path theory is most effectively used for testing a source and a target. You put the source here, you put the target here, it shows you what path you're taking, okay? Yeah. So yeah, the punchline is if you have an ergodic Markov chain, you can apply transition path theory to find these likely, transition paths. Okay, so I think that's a good amount of background. Now we can talk about applications. So there are many applications of transition path theory. In fact, I think originally it was used, or it was cooked up to for chemistry applications where they were looking at molecules interacting across classically forbidden regions, and they wanted to see how what the transition paths actually were. It can also be used to model oil spills, which is done by our very own scientists here at Erasmus, and it can also be used to model Sargassum transport. So that's what I'm going to tell you about today, my remaining time. So Sargassum, what is it? So in not so many words, it's a brown, golden brownish seaweed that floats on the ocean in huge rafts. So in this picture, you can see a moderately sized Sargassum raft floating in the Caribbean Sea. And why do we care about it? Well, for over a decade now, on a semi-regular basis, the coasts of South Florida and the Gulf of Mexico and islands in the Caribbean Sea are basically pummeled by Sargassum washing on the shore. And this is an issue because, well, it's an issue for a variety of reasons. For one, it stinks. And if there's enough of it, you have to close the beach for beachgoers. You can imagine that this is particularly a problem in islands in the Caribbean, where a big part of the local economy is tourism. So if they're constantly closing beaches, that's a non-trivial issue. And also, as far as the ecological impacts are concerned, if there's enough sargassum, it can kill fish, it can displace local wildlife that have habitats near the coast. So it's a problem, and people are increasingly interested in studying it. In particular, the general goal is to understand sargassum transport by the ocean. So there's a number of questions related to that. So how does it move through the ocean? Where does it come from? Where does it end up? That sort of thing. So that's kind of the application that I'm going to talk about today. So how do we actually do this? So what I'm going to describe today is a data-driven, or a data, a data-driven approach. And the data is given by the Global Drifter Program from NOAA. And the Global Drifter Program is just essentially what's shown in this picture. So there are these buoys, these drifters, scattered all over the ocean. And they have instruments on board that can measure various quantities. In particular, we know their location. So you have all of these drifters, and the idea is that we can use the trajectories provided by the drifters as a proxy for sargassum motion. So the obvious question is that actually a good model? Is it true that the drifters move like sargassum? So, good question. The first kind of refinement you can make that actually does a lot of heavy lifting is to think about the drogue status of the drifters. So a drogue is basically like an underwater kind of parachute. It's this big box that the buoys drag along underwater. And it's been shown, well, so first of all, sargassum drifts on top of the ocean, right? It just does. And it's been shown that wind is a significant effect on its motion. So therefore, the idea is that if you only look at the undrogued drifters, in other words, drifters that have lost their drogue for one reason or another, they're going to be more affected by wind because they don't have this sort of underwater parachute, if you like, and therefore they're going to be a more accurate model of the sargassum motion, and that's actually been demonstrated. So we don't necessarily just take all of the data and start going ahead. We actually have to prune it first to get rid of all the drogued drifters. So in this picture in particular, I've taken this from the NOAA website, and you can see that all of the drifters shown with the red dots are the undrogued drifters. So there's still quite a few of them. So we're not losing out on too many statistics by doing that. Okay, so we have all of these trajectories. So what do you actually do with them? So keep in mind this, I'm somehow talking about Markov chains, I'm somehow talking about transition path theory, so somehow I have to cook up a Markov chain out of these trajectories. So what I'm going to describe to you is how to actually do that. So you have this trajectory, which is just a list of points, right? The data from the GDP is given in a variety of formats, but the one that we use is the 6-hour interpolated version. So you actually have a bunch of points all along the trajectory, interpolated every 6 hours. Here's the thing: there's a few issues you have to be careful of. Some of these trajectories can be very long, but you don't necessarily want to look at really long trajectories because they're essentially, the longer the trajectory is, the more sensitive it is to initial conditions. So you don't necessarily want really, really long trajectories because A, you're not going to have very many of them, and B, it's going to be really unstable. So ideally, you'd like to have shorter trajectories, but the problem with having really short trajectories is something that I talked about way back in the day, which was the Markov property, right? So if your trajectory is too short, the Markov property is not going to be satisfied. You're going to have to worry about the memory of the drifter. So you sort of want medium length trajectories. So a way to actually characterize that is using the decoherence timescale of the ocean, which is roughly a day. And what that means is, for our purposes, what that means is that if you wait a day, a drifter will have essentially forgotten about where it came from, and it's sort of like it started over, like a Markov chain. So in order to make 100% sure our assumption that we're going to have a Markov chain satisfy the Markov property is actually true, is we're going to take trajectories to be of length 5 days. So 5 days is longer than 1 day, so we should be good to go for the Markov property, but it's not so long that two drifters that are close by will be really far apart, and it'll be too unstable. So it's kind of a good middle ground. So for example, you have this big long trajectory with a bunch of different data points. I'm going to segment it into 5-day chunks. So from here to here, that's 20 increments of 6 hours. That's 5 days. This is now a data point, if you like. So this is a data point for our creation of the Markov chain. And then you do that for every point on that line, right? So remember that the trajectory looks sort of like this, and now we don't know about that anymore. We just have these trajectories of like 5 days. Okay. Then you do it for every trajectory. Okay. So you've got dozens and dozens of trajectories. You segment them all into these 5-day chunks, and you get hundreds of thousands of these little arrows. I've drawn maybe 20, but it is what it is. So there's hundreds of thousands of these. Now, so you have these trajectories that are all the same length, and the idea is you somehow want to say, okay, I can push forward a drifter 5 days, and if I can do that over and over again, I can push it a long distance in increments of 5 days. Okay, so that's much easier to do because we have all these short-range trajectories. So here's the punchline. So you take your space, you take your domain, which for our purposes was the North Atlantic, and you segment it into these boxes. You discretize it, if you like. And there may be hundreds. There will be hundreds of these. So imagine hundreds of these little boxes, which, to be clear, are not actually squares because we're on the surface of the Earth, right? They're little chunks of a sphere, but to a good approximation, they're squares. And then we're going to define a Markov chain on a state space that is equal to the indices of these boxes. So I actually don't know how many boxes are in this diagram, but let's say there's 100. Then you're going to have a Markov chain with 100 states. So this is the first state, the second state, the third state, the fourth state, etc. So there's all these states in the Markov chain. And then to get the transition probabilities, all you do is you count what fraction of trajectories starting from any given box are going to any other given box. So let's say I'm looking at this box. Let's say there's 10 trajectories that start in it. If one of them goes here, then that entry in the transition probability matrix gets 1/10, right? It's just the fraction of trajectories that actually make it to those boxes is going to build up your giant Markov chain. Okay, so it's a simple counting exercise. Although I should mention that this does need to be theoretically justified, and there are theoretical justifications for doing this, which show that this Markov chain is actually a good approximation of the underlying dynamics. So you do this, and you're done, except you're not done, because in order to use transition path theory, you need an ergodic Markov chain, right? Remember, the only condition I mentioned is that you need it to be ergodic. So is this thing going to be a priori ergodic? No. In fact, in general, it won't be ergodic. In general, it might have islands, it might have cycles. You don't know. So what do you do then? Well, luckily, it's actually not that bad, because you can just look at the graph, the directed graph induced by your Markov chain, right? Every Markov chain corresponds to a directed graph, and you can extract the largest connected component, the largest strongly connected component. And strong connectivity is a sufficient condition for ergodicity, and there are algorithms which do this very fast. So you extract the largest strongly connected component, and then you actually do have an ergodic Markov chain, and then you're done. You have to be a bit careful about throwing away data, because that's unfortunately what it means to extract the largest strongly connected component. However, in practice, what happens is that you're usually throwing away states that are really close to the coast, where there's not very much data, or they're sort of in the middle of nowhere. So in practice, at least in this example, it doesn't matter too much that you're doing that, but I advise checking the size of the components you're extracting to make sure you're not throwing away half the data for no reason, essentially. And that's pretty much it. So once you do that, you pretty much have the Markov chain in question. There's one more thing you have to be careful about with respect to the edges of this chain. In practice, you have to impose an extra state, which they call the nirvana state, which kind of takes into account trajectories that leave the domain. I don't want to get into that too much, but you have to be a little bit careful if you have an open domain. But that's the gist of it. Okay, so in summary, can we construct an ergodic Markov chain? Yes, we can do that. The state space is a list of indices that represent these physical boxes that are actually chunks of space. Therefore, we can do transition path theory. So, just 40 short minutes later, I can now show you an actual result. Bam, there's a result. Okay. So what are we looking at? We're looking at the North Atlantic, and we're doing transition path theory, so we need an A and we need a B. B, remember, is the target, right? What's the target? Well, the target is in red, and it's the Gulf of Mexico. That's pretty well supported because that's where we see the Sargassum. It's in the Gulf of Mexico. The source is a bit trickier. In fact, the source is sort of an open question. So right now, it's placed here off the coast of West Africa, which is motivated by good reasons as well. But it's a bit of an educated guess, I would say. But that's the beauty of transition path theory, is that you can just do that. You can say, okay, here's the source, here's the target. Of trajectories that make it from the source to the target, how do they go? So I've covered the domain with a covering of 760 boxes, so there's a good amount of boxes there. And I found that the transition time was 9.81 years. And what we're actually seeing in the graph is the reactive density. In fact, the 8th root transformation of the reactive density, just to make it a bit easier to see. So what is this showing you? This is showing you, again, of trajectories that make it from this pink square to this red square. Where are they? So the bulk of them just kind of go, I would say, straight there, right? They take the kind of straight line path just across the North Atlantic, up through the Caribbean Sea, and up into the Gulf of Mexico. But very interestingly, there's a secondary path down here, which is sort of like a slower path, where they don't go straight there, they circle down, headed towards the Gulf of Guinea, and then they come all the way back around through the north of South America, and then back into the Gulf of Guinea. So this is the kind of thing, this down here is why transition path theory is so cool, because it's basically impossible to see that if you just look at the density, or if you just look at the stationary distribution. So it's pretty cool. Yeah, it's pretty cool. And in a way, that's kind of it, except there's a problem. There is a problem. And it's a subtle problem. It's a very subtle problem. The problem is this. So what I'm going to show you next is the same graph, the exact same graph, same calculations, same location for A, same location for B, same data, except instead of a covering by 760 boxes, I'm going to use a covering of 780 boxes. Okay, that's not many more boxes. Okay, it's not a radical change. But keep in mind what this graph looks like, and see what happens to the graph when I change the number of boxes by just 20. Bam. Isn't that crazy? So look at these. That's only a difference of 20 boxes, and the transition time is increased by a factor of a lot. It went from 9 to 180 years. So what to make of this? At first I thought that this was a deficiency of TPT, but it's not. This actually has nothing to do with TPT at all. It's just a consequence of using this binning method. It's a subtle issue, but the crux of the issue is that adding more boxes shifts all of them. Like if I try and squeeze in some boxes in the top left, it pushes every other box. And if you have sparse data, or sparse enough data like we do here, where not every square inch of the ocean is covered by drifters, that can have a big impact, and that's what we see here. Okay. It was theorized by me, I guess. Well, anyway, so it was theorized that a way to fix this would be to just use another shape, right? Why not use hexagons? The theory behind hexagons is that for hexagons, actually the centers between them are the same distance, whereas for squares, the distance between their centers are not the same, right? The corner ones are further away. So maybe it's not fair, right? Maybe squares are not a good timeline. So I repeated this calculation with hexagons, which is a bit of a pain, but you do it. And this is what I found. It's this exact same issue. So these are the same graphs with a covering of hexagons, but this is, I think, 820, and this is 840 hexagons. So it's a huge difference. And again, it's not related actually to TPT. It's just an issue that came up when we were applying this method. So the problem is that regular coverings, in other words, coverings by shapes that are all the same sizes, are not stable with respect to the transition times and other statistics. It's nice to use the transition time as a proxy for stability because it's a scalar, right? So here's the solution. In not so many words, the proposal is actually not too complicated. All we need is a binning algorithm, a way to cover the domain with something that takes into account the fact that the data is sparse. And what I propose to use is a Voronoi tessellation. And a Voronoi tessellation is a tessellation based on k-means. So k-means is a standard clustering algorithm. There's an implementation of it in pretty much every software package or library that you're using. So it's not too hard to do. Suffice to say, it clusters, right? So you have data, it finds clumps of data where where there's a lot of data, it draws a small box, and where there's not very much data, it draws a big box, right? So I do that, and I get this graph. So it's the same graph. It's the same A, same B, except now it's a tessellation by these kind of wacky shapes. But these shapes are all found automatically by k-means, essentially. You can see that the transition time is actually relaxed to 2.34 years because this pileup down here that we saw in the Gulf of Guinea is not so favored anymore in this covering. But to actually prove that this is doing something, this is kind of the money graph. So what this is showing you is the transition time, actually its logarithm, versus the number of boxes you're requesting in your covering. So even if you have no idea what's going on, you can tell something's going on in this graph, right? Because the squares and the hexagons are all over the place. Sometimes the transition time is 100 years, sometimes it's 10 years, sometimes it's 1,000 years. So how are you ever supposed to trust a graph with these coverings? How do you know that it's converged in some sense? On the other hand, the Voronoi covering, shown in black, is rock solid. It's rock solid. So this shows that you have to be careful about applying this method when you have sparse data, and in particular, this kind of covering will actually lead to a stable estimate of the transition times. Okay, I think I have a few minutes left, so I'm going to show you one more graph, but it's kind of complicated, so I do have to explain it. So again, it's the exact same situation, same A, same B, same drifters, same data, same covering. In fact, this is still a Voronoi covering. In orange, I'm showing you the forward current. So if you remember back in the blackjack example, I had those green arrows. these orange arrows are those green arrows, right? It's the same quantity. This is showing you the gradient. So drifters reactive drifters are being pushed in these directions. So you can see that there's a large current that goes basically straight, right? That basically goes straight from A to B. But this makes it really clear that there's this secondary path down here, right? You can see it. You can see it very clearly that it circles around towards the Gulf of Guinea, and then comes back around up to South America, and then up to the Gulf of Mexico. So that's really cool. In blue is something a bit new. So the stock quantity in transition path theory, this transition time TAB, only tells you the transition time from A. But what if you wanted to know the transition time starting from some other state? What if you had trajectories that had already left A, and you wanted to know how much time they had to get to B? That is this, TIB. I meaning any state. So you give me a state, I give you a TIB. This is a statistic that I developed, which tells you how much time you have left starting from anywhere. Okay, so it's similar to the remaining time, except it works from anywhere instead of just working starting from A. So the cool thing about TIB is that you can calculate TIB for every state, and then partition your domain according to those values. So for example, here I've done 3 partitions, and the darkest blue are those states which have the longest remaining time. So this is actually a non-trivial partition, because you can see that up here near the north of the graph, you have all the drifters essentially circulating. So it takes them a really long time to come back all the way around to get into the Gulf of Mexico. And down near the Gulf of Guinea, you have essentially the same problem, which is drifters getting pushed into the Gulf of Guinea. So a lot of times, the TIB can look like it's really just measuring the distance away of the state from B, but that's actually not the case, right? You can see right here, this has a comparable remaining time to something as far away as this, even though it's really close, because drifters over here are following the Gulf Stream, right? So they're not going to go down like this. They're going to go all the way around, pretty much, in order to get back to the Gulf of Mexico. So that's a new statistic I developed, and it's pretty interesting. Yeah, that's pretty much it. So I want to close out with some remarks. First of all, I have to plug my code. So I use the Julia programming language, which is a really good language, and I would recommend checking it out if you have never used it before. In particular, I've developed a package called ulanmethod.jl, and that's available for free. So if you want to do all this transition path theory stuff in your own problem, whatever it might be, you can use this package, and it'll do all the calculations for you automatically and pretty fast, if I do say so myself. So what are the outstanding issues? On one hand, the work that I've described doesn't necessarily advance our understanding of the physical mechanism of Sargassum transport. That's still another issue, in my mind a little bit orthogonal, but it is really the main issue. So the question is still, okay, we need a physical model of Sargassum motion. The state-of-the-art models are based on this Maxey-Riley framework, and there's still some work to be done there to actually get a really accurate model that's not just data-based. And you can also think about, so what I showed you with TIB is a partition, right? It's a way to divide the space into different zones. But you can think about other partitions, right? You can think about partitions that have different properties. Like, what if I wanted to look at the transition paths such that they all stayed in their own section? Like, what if I want to have a bundle of transitions that stay in one region and another bundle that stay in another region, right? These are the kinds of questions I'm actually thinking about right now. It's very interesting, and it reduces to some pretty non-trivial optimization problems that are not really in my wheelhouse, but it's something that I'm learning about, and is pretty cool. And I think that's about it. So thank you very much for your time.
very much. Questions from the room or the people here? Mike?
What do observations tell us about that transition time? I mean, you showed one plot, you had the two different actually three different tilings,
Yeah.
Squares and hexagons were all over the place, and then this Voronoi or something similar.
Sure.
It showed much more stable estimates of this transition time, but the transition times were also lower there, was somewhat,
That's right.
a couple of years, something like that, if I remember correctly.
Yeah. So for the transition time, which graph do I want it to be up right now?
Yeah.
So if you look at this graph, the thing about the transition time is that it takes into account every path. So there's this direct path, and then there's the one that's sort of revealed in the southern area that kind of loops around like this. So the thinking is that 9 years is probably a bit of an overestimate because this particular tiling favors this pileup down here a little bit too much. So the theory is that this tiling, so there is a pileup in the Gulf of Guinea. That's just where drifters are going, and the theory is that this tiling favors it just due to basically the shape of the data. So I think depending on which path you're focused on, you can get a relatively wide range of transition times. But I think the lower ones are generally thought to be more accurate.
Okay, but sort of direct observational evidence of Sargassum.
Right.
Is that, is it 2 years sort of a reasonable time for Sargassum to cross the Atlantic? I don't even know how long lived this Sargassum is.
Yeah, I mean, I think
So I think in this case, we are not actually taking into account the time, right? So you have all the drifters together, right? So
yeah.
That's probably one extra thing for future to take into account the time, because actually the waves of Sargassum are every year. So there is a seasonality, but that's mostly from the biology point of view. But so probably 2 years still long, but
Yeah, but
the thing is that it gets stable. But
yeah, I mean, the 9 years is obviously too long. 2 years is also still long. But you go to the TID graph; those are showing you already. I mean, times. Well, you did not color that according to time, but the regions in light blue there, they have a transition time much shorter than maybe it's around a year.
Yeah, that's right.
And a year is more reasonable for Sargassum to moving from off the coast of Africa toward the Caribbean Sea.
Well, the other thing that makes it kind of hard to answer is like the question of where it's coming from is sort of
it's still
an
open,
question.
right?
So does it take that long? Well, good question. Yeah, does it?
Yeah, but you may want to say that actually, although the use of these unrock drifters, it's not Sargassum, but these transition paths that Gage is showing there, they have some observational support. There is this thing that is called, this observance satellites, it's called the Great Sargassum Belt, and they show a very clear path along the main transition routes over there.
So satellite images of Sargassum.
And there is some evidence of the existence of this secondary path. And that, I'm not a biologist, but that secondary path can have consequences for blooming, because they go into where is the Amazon River. They can get what they can get there, Josefina?
Nutrients.
Nutrients there, so they can grow.
And they also
contribute
get
to
into
that.
the Gulf of Guinea, that you also have river inputs there, so it's kind of more slow path with more nutrients available.
Yeah, in order to be able to talk about
That pollen too, yeah.
in order to be able to talk about Sargassum, there's more stuff that needs to be done. I mean, maxi-rate theory will be good for motion, but then you have to put in there some
I think Arthur has a
physiology component into modeling and all that.
Roland, I think Arthur has a question.
Yeah, I'm not sure, but I want to ask him.
Yeah, Arthur
yes,
has a question.
Please ask, activate your microphone.
Oh,
Hello. First of all, thank you for such a really good seminar. I really enjoyed your seminar and learned a bit here.
thank you.
University of South Florida has a prediction
Yeah.
group for Sargassum, so you may want to check out the
That's-
University of South Florida website because they've produced a lot of maps. Check out the publications they're putting in. Humanchu's been, tracking Sargassum. One of the questions I have to ask is, you're assigning these probabilities of the drifters moving from, your partition A to partition B.
Yep.
I think in the real world, those probabilities are not stationary. They change.
Absolutely.
There's seasonal influences of the currents, seasonal influences of the wind,
Yep.
etc. And I'm wondering, how robust are these results to the fact that these probabilities are probably not stationary?
Yeah, that's a great question. In fact, that's something else that we've talked about, is at least taking into account, for example, having at least two transition matrices, one for one season and one for another season. But yeah, that's a good point. We can also think about applying a version of transition path theory that has a transition probability matrix that is completely time dependent. That is something you can cook up, but then it's gonna be tough, because the finer grained your transition probability matrix is in time, the less data you have. So I think there's a bit of a trade-off there, but yeah, I mean that's a good point.
Yeah, I took a graduate course in stochastic processes, way back in the late 70s, early 80s.
Right.
And I was working for Tom Rossby at the time, and at that time we only had SOFR flow data.
Mm-hmm.
And I tried to apply some of the ideas I had learned in class for a project. And one of the major parts of that data set for the local dynamics experiment is when they put the drifters in, like in May, they predominantly moved to the west. 2 months later, the drifters predominantly moved to the east. And trying to deal with that was very difficult, so I kind of threw my hands up. It's really good to see that you've made this nice progress here, applying this theory to a real data set.
Yeah, no, yeah, you're totally right. That's a great point about the time dependence.
Yeah.
So, Arthur, we did compare with the observation from satellite from South Florida. I'll send you some stuff later.
Sure, that'd be nice. Thank you. Yeah, that's a good group there to compare to. They have some, they're doing some good work there.
Okay, thank you, Arthur. Then Hura.
Okay. I don't know if this question makes sense, but you said for Markov chains, they don't really work well if there's cyclical activity or islands.
Yeah.
So then, do they not work well in areas where you have a lot of eddy activity?
Yeah. So as long as the requirement. So yeah, the requirement you're talking about is the requirement that it's aperiodic. However, you can still use a Markov chain to model a periodic phenomenon as long as it's not purely periodic. As long as there's some chance that the cycle can be broken, even if it's small, then you're fine. Yeah.
So in the Gulf of Mexico, if you were looking at oil spills and
Yeah.
you have these eddies that pinch off, you can still use a Markov chain to kind of guess where the oil's going to go.
Sure. Yeah.
Okay.
Yeah, as long as as long as there's, as long as it's not 100% mathematically cyclic, as long as there's some noise, basically, then you're fine.
Okay.
Okay, do we have any further questions from the many people here, or the one person in Zoom? I don't think so. So then thank you all for coming. Come again next week. Thank you for giving a nice and somewhat special presentation here. We will meet again on Monday morning for another special ATM seminar here at 10 o'clock. And then next Wednesday, Mo Iskandarani has a visitor, but I'm still waiting for the abstract, so I don't know when that will be announced. And next week Friday we have again 3 student seminars, but this week Friday we have a day off. So that's all. Goodbye.
Thank you, Lola.